Okay, today I'm going to talk about global illumination. I've mentioned this a little bit in the earlier ones. Let me get a share screen going here. So global illumination, there's a whole big long blog about it you can have a look at. And we used this when we were looking at both the emissive surfaces and the area lights. For both of those, you had to, for the area lights, it had to be the mixed or baked. And for the emissive surfaces, we found it could either be baked or real time, either one. Now, what global illumination deals with is not direct lighting. Direct lighting is done by default. Direct lighting is where light comes from a light, hits a surface, illuminates it, and the lighting calculation is done based on the various angles and so forth. But indirect lighting has to do with how that light bounces around in the world. The way this is done is by pre-calculating. That's what the baking is, where the different light paths are calculated. In the lighting settings, we have the little auto generate, in which case this happens whenever you change anything in the scene. This can put a overwhelming computational burden on your computer, since it's constantly trying to update this lighting calculation as you're manipulating things. I recommend turning auto generate off and generating it manually. So the global illumination models how light is bounced off one surface onto another surface. This is the so-called indirect light. The default lighting without baking handles the direct light, the light that comes directly from a light to a surface and illuminates that. But adding this indirect lighting makes the world look more realistic. An example of indirect lighting is where you've got sunlight that hits a red sofa or a red object, and the white wall behind it takes on a kind of reddish tinge because of the light that is bounced off the red object. It's white light that hits a red object, red light is bounced off it, and that illuminates the wall behind it. Another example is where sunlight hits the floor of maybe the opening of a cave and bounces around inside it, so that inner parts of that cave are illuminated. I have two of these examples here. This one is, here we see a scene without global illumination. It has shadows. The objects are lit, sides facing away from the light are dark, sides facing towards it are bright, all of that. But if we go to one of these baked light scenes, here now we have kind of red and blue highlights that are the reflected light from the red object that illuminates this white plane down below it. And I do have the indirect lighting turned way up here. Another example is a cave. Here's kind of a cave setting where I have a light that is kind of turning around here, and you can see the bleed of the color of this white light that is reflected off the red object and illuminates the surroundings. This is the bleed. If I have a big bright yellow plane that's catching things, the yellow light is bounced off the yellow surface and illuminates the interior of the cave. I'll come back to these later and show you these in more detail. So traditionally, video games and other real-time graphic situations have been limited to direct lighting. This is changing rather rapidly as our computers become more capable. But the way that Unity does this is that we calculate the indirect light ahead of time. And we do this by marking various renderers within the scene to be light map static. 219.1 and before, it's called light map static. At some point between 219.1 and 219.4, they changed the label to contribute GI. So that's, those both mean the same thing. Now this computation takes time. It can act, with a big scene, it can actually take half an hour or more to calculate the lighting for that scene. But we generally do it ahead of time with this phase we call baking the lighting. So the baked lighting essentially produces these baked light maps that contain the indirect lighting that is then applied into the scene at runtime. Baked GI, because it has more time, generates better shadows generally, specifically for area lights and for the indirect lighting. Unity 5 added something called Precomputed Real-Time GI, and sadly, this has been deprecated. It's going to disappear in Unity 2021. They are promising that they're going to fix it. These places down here will tell you more about it. But it's still a feature in Unity 2.19 and 2020. It will disappear and be replaced by something, is what they're promising us. And what the real-time lighting does, like the baked lighting is kind of static. Once you've lit a light, it's there, and its indirect lighting is applied to the scene. And if you happen to change that light, it doesn't change the indirect light that's already been cast out into the scene. But real-time has the ability to do this. And it does this by not just computing what the light is, it also computes all the possible light bounces in the scene at the time that it's built. And it encodes these bounces for use at runtime. At runtime, we can populate these light bounces with real-time light. So essentially, for all of these light map static or contribute GI objects, it answers the question: if any light hits the surface, where does it bounce to? And this is all saved into information either in the GI cache, if you're doing auto, or into folders in your Unity editor in the project view. At runtime with real-time, the lights that are actually present with their color and their position are fed into these pre-computed light propagation paths. It's very, very cool. This means that the number and types of lights, their position, their direction, their colors, their brightnesses, their range, all these can be changed, and the indirect lighting will update accordingly. And I'll show you examples of that later. The pre-computed real-time is because it is something that has to be populated at real-time, is not as high resolution as the fully baked lighting. It's generally coarser. You can make it as fine as you want, but it is a computational load. It also does not happen instantaneously. So there are artifacts that you can see as the real-time lighting catches up to the change of the scene. And there's some settings that we can set for how it will happen. Generally, these artifacts are not noticeable, particularly if you're on relatively strong hardware. But if you are programming for target platforms like phones or other things with constrained resources, it's generally better to use the fully baked GI for runtime performance. This is all done ahead of time, and it's just textures that are applied to your different materials, and it's very, very quick. But pre-computed real-time does cost you something in performance. As I mentioned, both the baked GI and the real-time GI are limited to light map static or contribute GI objects. And these things can't move. So if you're going to, if you want to light moving objects, you're going to have to do something involving light probes. And I'll show you examples of those in a little while. Light probes are positioned within the scene where the light is measured during that bake process. So these are spots where the lighting, either baked or real time, is captured. And the non-light map static moving object can then catch its lighting information by sort of interpolating these light probes. Uh, uh, there's light probes. Whoops. Uh, Light probes is here, and I'll show you these light probes in a little while. GI probes. So all of this goes forward with the lighting window. It's a window that we pull down and dock if we want it. I have talked about it a little bit, but I'll go into it in more detail here. The default settings are generally appropriate, but there are various things you can adjust that will either make your scene bake faster or will affect the improve the quality and so forth. I'm going to pause this at this point, and I'll continue discussion about the lighting window in part 2 of this video. So I'll stop the sharing here, and I'm going to end the recording. And this is part 1. There will be more, and I'll stop right here. See you in class. Bye.